Hello everyone. In this video, I'm going to continue to discuss um, the methodology to turn the low pass filter into a clean circuit. And in the last video, I've shown you we can convert the low pass filter, a lump element version of the low pass filter, in a clean circuit. And the clean circuit will appear like this. It has an open circuit stop. So in this case, it is very easy to implement because you have a ground here. The ground here is available in a normal printed circuit. And with the open circuit stop, all you need to do is to find the right riff to match with this ohmic, this impedance 70.3 ohm. And we need to make sure the guide wavelength is about 90G by 8. Yeah? I mean, you need to make sure the length of the stroke is equivalent to the guide wavelength divided by 8. And you also have a series short circuit stop, and this one is going to uh, realize the inductance. But there is a problem with this circuit. First, in microstrip, it is not easy to implement this item. You might end up with a series transmission line, but you need to guarantee the length of this short here is sufficiently short, so it won't affect, it will not produce any transmission line effect here. So there's a limitation with the circuit. And this is the Richards transform circuit, but we cannot use it immediately. So what we can do now, fortunately, Kuroda, a Japanese scientist, has come up with an idea. He said there is a way to convert the series short circuit stop into the open circuit one. All we need to do is to follow this idea. First, whenever you come across with an open circuit stop like this, a transmission line like this, so this is V1, and you have an open circuit stop connected to the end. And uh, the open circuit stop has a characteristic impedance V2. So immediately, you know a variable called n square is equals to 1 plus Z2 over Z naught. Z naught 2 over Z naught 1. So you calculate this first. And afterward, you can rewrite this structure into this one, a short circuit stop. And the transmission line characteristic impedance is going to be V naught 1 over n square. So over this vector. And the characteristic impedance of the short circuit stop here is going to be V naught 1 over n square. Sorry, I got it wrong. Here is 2. So this conversion allows us to convert the open circuit stop into short circuit stop. But we need a little bit of line segment here. And the line segment here is nano G divided by A. And same here, nano G divided by A. All the line segment here is nano G divided by A. Yeah, here, nano G divided by A. Same here, nano G divided by A. So you need this, and you also need another um, identity which allows you to convert all the short circuit stop into open circuit stop. The idea is, suppose you have a transmission line here, and so same, we have the length here, lambda g divided by A. So you use the formula to convert it. 1 plus V naught 2 divided by V naught 1. And then, with this in mind, you can convert this structure into the one with open circuit stop. So n square 2 1, and then here is n square V naught 2. So it's very simple. Yeah, to be honest, you don't really need to know. You just need to know what this the link here is assumed to be uh, by default lambda g divided by A. So you don't really need to. So this is something that you need. You don't need to worry about the original version of Kuroda identity. Uh, this one is good enough for you to solve all the problem. Now, we are going to take a look in the example here. And this was the example left from the last video. So what we need now is to convert all the short circuit stop into open circuit stop. So for this one here, it's difficult enough, but don't worry. What we can do here is we add an artificial line segment here. And this line segment has the characteristic impedance 50. And the length here is obviously lambda g divided by A. Now, we can also add the same here. And then 50. And by adding this box at the input and output, you are not going to affect the behavior of this filter. The only thing that you need to worry about is the delay, but in general, it's not going to affect much. Now, if you take a look in this arrow shape, yeah, the short circuit stop together with this line segment here, isn't it very similar to this one? Yeah, I'm talking about this. is the same here, almost the same. So in other words, you can immediately convert this into this one. So I'm going to do it here. So I'm going to rewrite this. So again, the middle line segment is not going to change. It will remain 70.3. But here, you are going to convert it into this one. So new line segment here. And the value here is going to be n squared times 0 and 1. And before doing this, let us calculate the value of n squared. N squared is equal to 1 plus, according to here, is this transmission line divided by this. This means 50 divided by 167.4. So if you do it very carefully, you get 1.2987. So with this in mind, you will need to calculate the impedance here. The impedance here is going to be n squared times the stop impedance. So this means n squared times 1.298, right? Times the stop impedance here is 162.4. So if you do it very carefully, then you will get 2.17.4. 2.17, sorry, 217.4. So 217.4. Now the stop, you need to find the stop impedance. So we write it carefully. And this one is going to be n squared times this one. 0 is 50 ohm here. So times 50. So 1.298 times 50. So if you do it very carefully, you got 64.9. So the ohmic here is 64.9, and this is done because the left side of this circuit is symmetrical with this one. So all you need to do is to mirror this part according to what you have on the right. 217.4, and then this one, the ohmic is 64.9. So this is done. This is our filter. This is the expected filter, yeah. So I'm going to make it more clear, yeah. Here is a little bit messy. So yeah, it's easier to read in this manner. So n square v not 2. Okay? So your answer is here. This is the answer. So if you have any question, please leave the question in the comment section of this video. Thank you very much for your time. Bye bye.